Okay, so I'm going to talk to you a little bit about how to compute X and R bar charts. This is what we did in class on March 24th, and I'm going to go into a little bit different detail, but basically cover the same thing. So what you see in front of you is a picture of what we had in class as a handout, although in class these columns over here were filled out, but I wanted to show you how to do it in Excel. We will ultimately have the same numbers as you probably have in front of you right now. So as I said in class, this is a sum of hour 1 divided by the number of boxes, or an average if you will. So if I click on this box 6 right here, L6, you see average of C6 to K6 comes up in there because that's the formula I have in there. As well, if we go over here to this box, you see we've got the max minus the min, because this column is the range. So this column is what we call X bar, or the mean for each of the samples, hour 1, 2, 3, up to 12. And this is the range, the high minus the low. So what I want to show you how to do here is how to calculate this yourself in Excel. You could do the same thing by hand, but of course I think it's a little easier in Excel. So what I'm going to do is just click on this box where I want to compute it, and I'm going to go right up here to this f of x insert function. I'm going to click on that, and I'm going to type in average because I know that's what I'm looking for. So average comes up, I double click on it, and it brings up this function argument box, and I'm just going to highlight this row of data right there. So now it's going to give me the average of C7 to K7, and the average I can already see right here is going to be 16.77, and I'm going to hit OK. But because I know I've got this rounding problem, I'm going to also type in here round, open up parentheses, and then put comma 2. So that means I want it to take the average but round it to 2 decimal places. And if you notice on this one, I didn't have round in there. I mentioned that in class yesterday. I did this before I learned about rounding, so I'm going to add that in. And now I'm going to I've got this, so I could do it, I could retype it every single time, but that's kind of a pain. So I'm just going to copy it down. I'm going to grab this little box right there. So see, I get the fat plus sign, it turns into a skinny plus sign, and then I just carry it down. And now I've got the average of all of those different hours. Now you'll notice that this all turned red, and I don't want it to be red, so I'm going to change it back to black and then make this one green, but you got the idea. Now I also want to show you how to do the range. So I'm going to go over here. Now you notice it's in this box already, but I want to show you how to make the formula, and essentially, since there is no command for range, I'm going to do the max minus the min. So I'm just going to do equals max, and I'm going to open up my parentheses. I'm going to highlight this section, close up my parentheses, minus min, open parentheses, highlight the same thing again, close my parentheses, and hit return. So here the range is the high minus the low, which is going to be the highest number here looks to be 17.2 minus the lowest number here, which must be 16.2. So that's where 1 comes from. Again, we pull it down, and we've got our average there that we need. Now what to do with this? We need to take the average of our X bars, because we're after X double bar, and in class I showed you that the sum of this was here, and then I put the average in this box. So I'm just going to go ahead and skip right on to average, and again I'm going to do the same thing. I'm just going to highlight that, hit return, and I've got 16.3, and then I also want the average of the ranges, so I'm going to go and put this. So now you can see this is where we came up with the average and the range. Now I'm going to move on to what to do with this. So now we've moved down to the step 3, because step 2 is computing the standard deviation. And for these problems, the standard deviation is going to be given to you. So you're not going to need to do it. But in this problem here, we need to use x double bar, we need to use z, and we need to use the standard deviation of x bar. So first, let me show you how to get the x double bar number. The x double bar number is going to be that average that we took from above. So right up here, we took this number. This is the same as x double bar. So I'm going to highlight that, and I'm going to bring it down here, and I'm going to put it in here as 16.03. Now you'll notice in the textbook this is 16, so the actual number is 16.03 because I made up the numbers to go with it. The textbook didn't provide the data, so we're going to just use 16 for the purposes of this problem, but the actual number is 16.03. So we're going to change this now to 16.0, and if we rounded it, that's what we would get. So the next thing we need to calculate is going to be this right here, this standard deviation of x bar. So down here I made this little formula. I took the standard deviation of x bar, and I'm telling you that it equals the standard deviation of the sample divided by the square root of n. So in this problem, I know that the standard deviation has the value of 1 because that's the way it was done in the textbook, and up here I've stated that the standard deviation is 1.02, but we're going to use 1. So I'm going to insert here another formula. So first I have my division equation here that I've inserted, and then up here the standard deviation I know is 1, and I'm going to divide by the square root of n. So I have to go up here, I get my radical sign. Now n is the size of the sample, and in this case the sample size was 9. Now if you remember, we had 12 different samples, but the sample size, which is the number of boxes, in this case is 9. So we've got 1 over the square root of 9, which should indeed equal a third. So we're going to put 0.33, and that is the number that we're going to put in this space here, the standard deviation of x bar. Now the other thing we need for this is z, and z, using the z value of 3 means we want to create limits that consider 99.79% of the occurrences. So z in this case is going to just simply equal 3. So I have z equals 3, and then I've got now the standard deviation of the sample during the standard deviation of the sample, and I have x double bar. So now I can plug the equations into here, into this equation, and I'm going to do that. So I have typed it in here as the upper control limit of x bar is going to equal x double bar plus z times the standard deviation of x bar. So 16, which is the mean of means, or x double bar, plus z, which we say is 3 because we want to consider plus or minus 3 standard deviations, which is 99.79% of the observations, multiplied by the standard deviation of the sample, which is 0.33. And that's going to give us the value of 17. We're going to do the exact same thing down here for the lower control limit. So you can see here that I have copied everything down here, and you see that. So as you can see, what I did, I just copied the stuff down here, and now I have a minus sign. So now instead of it equaling 17, it's going to equal 15. And what we have just computed is the upper and lower control limits for this sample. So what does that really mean? Like, why did we do this? Let's go take a look at the data. So what we said is that most of these samples, these averages, should fall between 15 and 17. That's the normal variation. If we have more variation than between 15 and 17, we might have a problem. So notice this one here. This one might be a problem. So these two may be a problem because if you notice they are 14.7, which is a little bit lower than our lower control limit of 15, and 17.21, which is a little bit higher than our upper control limit of 17. And so now what we're going to do is look at this in a graphical depiction. There I've graphed all the points, and I can talk about each point and where it fits within an upper and lower control limit. The final bit of this video or this concept is these last two questions, questions 1 and 2. Does the sample appear to be in control? So I mentioned this a minute ago. Our sample is not completely in control because indeed samples 11 and 12 are out of control. We notice that both because they're outside of our upper and lower control limits, and if we look up above, we see that these numbers as the means, both the 17.21 is higher than 17, and we notice that the 14 is lower than the 14.7 is indeed lower than than 15, which is the lower control limit. So if we go down below, I've written that out so you can see that our sample is not completely in control. Indeed, samples 11 and 12 are out of control. And then what may be the assignable cause of variation? So we don't really know, but this is some of the difficulty in management, and I would suggest to you that when you see something like this in the workplace, you go to the shift and you watch what goes on, and you probably will have your answer by the time you leave. It may be that people are getting tired at the end of the day and making mistakes. And one last piece of this, I want to show you another graph of the same information where I've connected the dots. So what you have here is just another graph really of the same thing. I just put the line in here, and I think it's easy to see here that you've got a problem right here, and then again you've got this problem outside of here. Alright, now I'm going to move on to what is below, which is doing the same thing but using the R bar to do so with. So now we're moving on to a different way of calculating the X and R bar in this practice here, if you will. It's just another way that this information may come up. And in here what you notice is we have a process that has an overall average of 50 units. So we know that the X double bar then is 50. And the process standard deviation is 1.72. The sample size is 5. So now we're going to determine the upper and lower control limits using a method very similar to the one we had done on the previous page. However, this time we don't have to calculate the X double bar because that's provided for us. So you notice over here I've got a couple things calculated. So first of all, your handout just has this stuff over here. It doesn't have what I've written here. So the first thing we need to do, step number 1, is to calculate the standard deviation of the sample. Because this 1.72 is the standard deviation for the entire population. So we need to convert that over to a sample standard deviation. And we do that by taking the standard deviation and dividing it by the square root of the sample size. And you notice here that the sample size is 5, even though it says, you know, all this business about 50 units, etc. So don't be swayed by that. So we calculate this 1.72 divided by the square root of 5, we get 0.77, and then we add it in a similar fashion that we've done in the past, where we take 3 standard deviations of this and we add it and subtract it to our upper and lower control limit. So what this tells us is that the process is considered in control if the X bars for each of the samples that are taken, each of the 5 samples that are taken, fall between 52.31 and 47.69. So a sample that might fall out of that, say for example if you found one that was 46, the process then would be out of control. Now here I say, now consider this using 2 signal limits. So what you would do is the same exact process as I have here. It's just that you would change this 3 to, of course, a 2. So I'm going to pause and let you take care of that. And now we're going to move on to using this table. So there's a table in your textbook, and it looks exactly like this, and it has factors in it which allow us to calculate upper and lower control limits without having the process standard deviation. So we can use these only when we want to calculate something at 3 sigma. So z equal 3. I can't write too well with this mouse, but doing the best I can. So when z is equal to 3, then and only then can we use this table. So what we have down here is slightly different formulas that include, of course, these factors. So if we wanted to compute the upper control limit for x, we would need the a2 factor and r bar. And we need x double bar. So down here in this problem, we see consider a process where 12 samples, each containing 5 parts, are taken in a process. The x double bar is 10.005 and the r bar is 0.0115. What is the upper and lower control limit of the mean and the range? So let's go ahead then and do the upper control limit for the mean, which is going to be UCL will equal this number here, this 10.005, right? Because that's what x bar is, so we'll do. Now we go up and choose the A2 factor, and the tricky part here is making sure you know the sample size. So in this I tell you that each of the samples contains 5 parts. That means the sample size is 5. So we choose this 0.577. So I've changed it so I could type the letters, and so it wasn't so messy. So the upper control limit then is going to be 10.005 plus the quantity of 0.577 times 0.0115. That would be the upper control limit. And then the lower control limit would be computed in a similar fashion, but we would just have a minus sign here. And you can see that I've calculated it out for you as well. So our limit is pretty tight here, but you'll notice that the value of x double bars is pretty small as well. So now the next thing we want to do is calculate the range for our sample, the upper and lower control limit of the range. So we'll do that in a similar fashion. However, we're going to use this UCL for the range, which is going to involve D4 and R bar, and then the LCL for the range here is going to be the D3 and the R bar. And then, as you can see, I've calculated here for you, we end up with an upper control limit of 0.02 and a lower control limit of 0, which is not at all that surprising, because whenever you have a small sample, I guess less than 7, your lower control limit is going to go to 0 because the factor is also 0. Alright, so now we're going to move on to the next part of this handout, which is calculating R bar by hand for the first page that we had begun with. It will be a very similar computation as we had done on this first page here, but now we're going to do it slightly differently. We'll use the table to calculate both R bar and X bar for this exact same data. So now when we move on to this problem here, it's the same. It's based on the same data as before, right? So we've got our x double bar, which is equal to 16, because that's what it was on the previous problem. And when I say previous problem, I'm talking about the problem back on the very first page of this handout. I'm going to scroll all the way up here to the very first page so I don't confuse anybody. So I'm using this number here, this x double bar right here. So that's the x double bar. This is my sample size. 9 is my sample size, and so I'm going to get an A2 factor commensurate with that. So let's go back down here where we were. You'll notice I've already plugged in some of the numbers just so that you make it a little easier for you to see. You don't have to wait for me to type it all out. So we've got 16, that's our x double bar, plus 0.337. Now this is our A2 factor, and we have gotten that from our table right here. Now, in the previous case, we had an n of 5, so we chose 0.577. In this case, however, we have an n of 9, so we're choosing 0.337. So let's go on back down here. And the range, if you remember from before, was 2.2. So we calculate this out. Go ahead and do that. And you get 16.74 for the upper control limit and 15.26 for the lower control limit. Now, we could also calculate the range, upper and lower control limit, which we could do right down here. Well, excuse me, the way I have it written here, that the range should be down here, so we're going to just move this right up here. And then we'll go ahead and calculate the range just below. So remember from before, the upper control limit for the range is going to be the D4 factor times R bar, and the lower control limit will be the D3 factor times R bar. And I'll fix that up here real quick. So I need to get my D3 and D4 factor from here for an n of 9. So I'm going to come across here and I'll see that this is 0.184 for my D3 factor, and for my D4 factor I've got 1.816. So we'll go back down here. So we have 1.816 times our R bar, which was 2.2. And then for the lower control limit, we have 0.184 times 2.2. So there you go. That's the upper and lower control limit for the range. Now, how does the upper control limit for the ranging mean differ? Well, the upper control limit for the range is a measurement of dispersion, how many points are well spread out, versus the mean, which is the measure of central tendency. And what do all these computations tell us? Well, it tells us a little bit about our data. It tells us that our samples, our last two samples, 11 and 12, were too low and too high overall, but it also tells us that sample number 1 is out of control with respect to the range. So we've got somewhat of a problem with our data up above. So what does all this tell us? Well, it tells us that the X bar chart tells us that the central tendency, if you will, should be right around 16 plus or minus 1, and the R bar is a measure of dispersion, so it tells us how dispersed our data ought to be. So hopefully this is a nice review for you for the variable charts, and let me know if you've got any questions.